Hey! Alright, so in this video we're going to be talking about Taylor's inequality. In the last video we talked about this idea that we start off by saying if f of x can be represented by a power series. And then we launched into the rest of the video and we talked about how to represent f of x as a power series and what the radius of convergence would be, but we still never answered that question of when can we actually do this. That's what Taylor's inequality in this video is all about. Which brings us to this note. We can find a Taylor series for several functions, but how do we know that this Taylor series actually equals the function? Because we made this big assumption that we could actually do this in the first place. So let's explore when this assumption is actually valid. Now, I just want to give you a heads up. This video is going to be a lot about proving things, and it's really supposed to highlight the importance of proving mathematical statements. Mathematics is about creativity, and it's about exploration, and it's about trying things out and seeing what happens when you do certain things. But along with all of those comes this idea of actually saying something concrete. This is when we can do these things. And not only saying this is what we can do and this is when we can do it, but also, and here's the big one, why we can do these things. It's explaining to someone this reasoning behind why you are able to actually say the things that you say. So, that's what proofs are. The proofs are the why. So in this video, we're going to talk about Taylor's inequality. We're also going to prove Taylor's inequality, and we're going to be proving a lot of statements and justifying this whole if we can do this, if we can represent f of x. Well, we will find out exactly when we can do that. In order to do that, we do need to start off with a definition, and this is a familiar definition because it's a remainder. It's not a remainder of a series, so to speak, in the same way as we had before, but it's a remainder of a Taylor polynomial. So remember last time we were seeing that a sum was equivalent to a partial sum in addition to a remainder. So the remainder was the same as the sum minus the approximation. That's the same definition that we're making here, but instead of S sub n, we're using T sub n. So R sub n is S, the sum, which is our function, minus our approximation, because our function and our approximation, our Taylor polynomial, are both functions of x. So too is our remainder. So here's where our definition comes in. If we let R sub n of x be equal to f of x minus T sub n of x, that's what we did here, then we call R sub n the remainder of the Taylor polynomial T sub n of x. So let's just get an idea of what a remainder looks like. In the last video we found a Taylor polynomial for e to the power of x. We found a third degree one. Well, remember, e to the x, this is a sum, as n went from 0 to infinity, of x to the n over n factorial, which means that e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 5th over 5 factorial plus x to the 6th over 6 factorial, and I think you get the idea. Well, when we do this, we're actually isolating. Here's t sub 3 of x, and the remainder is everything that's left. Here's our remainder. Our remainder is everything to the right of t sub 3. We call that r sub 3. Anytime you have a sum, then what we are finding is that our sum is equivalent to our approximation in addition to our remainder. So, the remainder for the third degree polynomial for f of x centered at 0, f of x is e to the x centered at 0, is r sub 3, which is x to the 4th over 4 factorial, plus x to the 5th over 5 factorial, plus x to the 6th over 6 factorial, etc. Cool. So we dealt with remainders in the past with talking about how good an approximation might possibly be. But we want even more than that right now. We want our approximation, t sub n, to be so good that as n gets bigger and bigger and bigger, it really is just the function. It's not close to the function, but it is the function when n grows larger and larger and larger. So r sub n, our remainder, is this, again, idea of controlling how good our approximation and our estimate actually is. A lot of the rest of the theorems here, and a lot of the proofs, are going to be dealing with controlling r sub n. Here's our first theorem that we're actually going to deal with, and we're actually going to prove. If f of x is equal to t sub n of x plus r sub n of x, which is not a bad assumption at all, we can always just write f of x equal t sub n of x plus r sub n of x. We can write down something, but we don't ever really know if f of x is equal to the Taylor series, but we can actually just say, well, it's some approximation plus a remainder. So we can write this out. If f of x is equal to t sub n of x plus r sub n of x, and we know that the limit as n approaches infinity of the remainder is actually 0 for x, all the absolute value of x minus a's is less than r, so for all the x's in the interval of convergence, or within that radius of convergence at least, then the conclusion is that f of x is actually equal to a limit as n approaches infinity of t sub n of x on the interval absolute value of x minus a is less than r. This is a pretty big statement to say that our function is actually the limit of its Taylor series, or a Taylor polynomial. And the limit of a Taylor polynomial is a Taylor series, hence my slip up. So, let's try to prove this. So we are actually assuming that the limit as n approaches infinity of r sub n of x is 0. This is an assumption for the x values satisfying absolute value of x minus a is less than r. So we are actually using this as an assumption. Let's find the limit as n approaches infinity of t sub n of x. We want to show, we'll write this out, we want to show that the limit as n approaches infinity of t sub n of x is f of x. Well, let's consider the limit as n approaches infinity of t sub n of x. Well, we know that this is true, so if we subtract the remainder from both sides, then we can actually even say that t sub n of x is f of x minus our remainder. So let's use that fact right here. Let's substitute t sub n of x for f of x minus our remainder. Now the limit is distributive over subtraction, so we get a limit as n approaches infinity of f of x minus a limit as n approaches infinity of our remainder. But we know that the limit as n approaches infinity of the remainder is 0. So this part's 0. And we're left with the limit as n approaches infinity of f of x. Well, there's no n's in f of x, so the limit as n approaches infinity of f of x, that's just f of x. So this proves our theorem. We've always finished a proof with a little box. The box actually means QED. I don't speak Latin, but So my pronunciation is probably going to be off, but to my understanding, this means quod erat demonstratum. It's a way to say, it has been shown. Again, signifying, we've shown the proof. We are done. Alright. So what we've really just stated, and I'll write this down here in green, is what we've just shown is that f can be represented by a Taylor series when the remainder limits to 0. But we still don't know when this happens. In order to do that, we actually need to introduce a little bit more theory. So this is still the open question. We were trying to, again, answer the big question about when can f be represented by a power series, and we've just found that f can be represented by a power series when the remainder limits to 0. So the new question is, when does the remainder limit to 0? As I mentioned, in order to get there, we need to actually take a side step and and try to go with this new theorem, the weighted mean value theorem for integrals. Alright, so the weighted mean value theorem for integrals says, if we have these two continuous functions, f and g, and they're continuous on the closed interval from a to b, and g doesn't actually change sign on a to b, excuse me, then there exists a number c somewhere in a and b such that when we integrate from a to b of f of x, g of x dx, we could actually have really just integrated g of x as long as we have some value that we just plug into f. It's kind of like saying, let's not integrate the product of these two functions, let's just integrate one of these functions and let's assume the other function is constant. But that's not really an assumption, as long as we can prove this statement. So, let's prove this weighted mean value theorem. So anything after if and before then, we can assume. So we get to assume that f and g are continuous. Assume f and g are continuous on the closed interval from a to b. And also that g does not change sign. On that same closed interval from a to b. We want to show that there's some number, there exists some c, could be a, could be b, could be any number in between, such that when we integrate from a to b of f of x dx, gx dx, we could have instead just plugged in c into just f and then integrated g. So, we know that this function g does not change sign. So, let's suppose, without loss of generality, this is a big statement in math that says we can assume this and it doesn't actually change anything. We can assume that g of x doesn't change sign and that it stays either positive or 0. It doesn't go to negative though. Alright, well, we're going to try to use all of the theory that you've seen in differential calculus and integral calculus in order to prove this. So let's go way back to kind of halfway, right when you're changing between differential and integral calculus. You talked about this theorem called the extreme value theorem. The extreme value theorem. Now, the extreme value theorem says that if you have a function that is continuous on a closed interval, then that function attains an absolute maximum and an absolute minimum somewhere on that closed interval. Now we know that f is continuous on this closed interval from a to b. So we can conclude from the extreme value theorem that f has an absolute minimum value let's call it m, little m, as well as an absolute maximum value, and let's call it capital M, somewhere in the closed interval from a to b. This means that because little m is the minimum value and big M is the maximum value, little m is less than or equal to f of x, which is less than or equal to big M for all x in this closed interval. Big M is the biggest possible output, little m is the smallest possible output, and so big M is is greater than or equal to f of x, which is greater than or equal to little m. Now we also know that g of x is at least 0, so we can actually say that, let's take this inequality, m is less than or equal to f of x is less than or equal to big M, and let's multiply everything by g of x. Because g of x is not negative, it does not flip the inequalities, and it maintains the exact same inequality statement. M times g of x is less than or equal to f of x times g of x is less than or equal to big M times g of x. Now, for all the x's in between a and b, we can now say that, well, we can integrate. We can integrate along every single one of these different pieces. We can integrate the left side, integral of m g of x dx, and we are integrating from a to b. This is less than or equal to an integral from a to b of f of x g of x dx, which is less than or equal to an integral from a to b of big M g of x dx. This is a statement that we get from all of these integral properties from when you first learned about definite integrals. I think when you learn about definite integrals, you typically learn like 6 or 8 different or 9 different properties of definite integrals. This is actually one of them. It's slightly modified, but it should all fit. Now we do have constant multiples in here, so we can actually pull out this little m and get little m times an integral from a to b of g of x dx is less than or equal to an integral from a to b of f of x g of x dx is less than or equal to big M times an integral from a to b of g of x dx. Now we know a couple things about g of x. We know that it is either positive or it is 0. If it happens that g of x is 0 the entire time between a and b, then our definite integral would be 0. Then what we would have up here would be 0 is less than or equal to 0 is less than or equal to 0. And our theorem is true. We would have shown that, well, the integral from from a to b of f of x g of x dx, I should back up. This is not necessarily true. We would get m times this piece, which would be 0, big M times that piece, which would be 0, but the middle piece we would not be quite so sure of. And so we would say that m, little m, times 0 is 0. This is less than or equal to an integral from a to b of f of x, g of x, dx, which would be less than or equal to 0. Well, if the integral from a to b of f of x, g of x, dx is less than or equal to 0, while simultaneously being greater than or equal to 0, then the integral from a to b of f of x, g of x, dx must be equal to 0. Because the integral from a to b of f of x, g of x is equal to 0, and because the integral from a to b of g of x dx is equal to 0, our statement would say that 0 is equal to 0, and that would prove our theorem. But what about if the integral from a to b of g of x dx is not 0? If it's not 0, then the integral from a to b of g of x dx must be greater than 0. Because our function is never negative, then our integral can't possibly be negative, so our integral must be positive. Then let's take this same inequality right here and divide everything by the integral from a to b of g of x dx. Then our inequality, m times the integral from a to b of g of x dx, is less than or equal to an integral from a to b of f of x, g of x dx, is less than or equal to big M times an integral from a to b of g of x dx. This implies that because we have an integral from a to b of g of x dx, which is positive and not 0, means we can divide by it, and it wouldn't change any of the inequality symbols. This would imply that little m is less than or equal to an integral from a to b of f of x, g of x dx, divided by an integral from a to b of g of x dx, which would be less than or equal to big M. Now, we actually have another theorem that you probably learned quite a while ago called the intermediate value theorem. By the intermediate value theorem, this theorem says if you have a function that is continuous between a and b, and at a you get a value of f of a, and at b you get a value of f of b, then for every value between f of a and f of b, your function actually attains that value. So for example, if you had a function that was continuous, and at 0 it was equal to 0, and at 1 it was equal to 1, then your function would attain every single value between 0 and 1. It would attain 1/2, it would attain 1/3, it would attain 0.1156734372. Who knows? By the intermediate value theorem, we actually have a continuous function, so there must exist some value c in between a and b, such that, now, remember little m is an absolute minimum of f, big M is an absolute maximum of f, and so our function f has to obtain every single value between little m and big M. Namely, it has to attain this value. So there's some value c in between a and b such that f of c must be equal to this crazy integral. I'm just going to say, I'm going to call this star. Because this is true, we must have that. Let me actually just go back and write all this out. Because this is true, the integral from a to b of f of x g of x dx over the integral from a to b of g of x dx must be equal to f of c. So because this is true, then if we multiply both sides of this equation by the integral from a to b of g of x dx, then we get f of c times the integral from a to b of g of x dx is actually equal to the integral from a to b of f of x g of x dx. This proves our theorem. I mean, it doesn't quite prove the theorem because there is this little piece up here where we assumed g of x was greater than or equal to 0. But this is an argument that we make in mathematics called a parallel argument. By parallel argument, if we actually had that g of x was less than or equal to 0, then we could run through the entire statement, except it would just switch the inequality symbols everywhere we would see them, which would still lead us to the exact same conclusions. So, I'm not going to write through all of that, but I encourage you, check this out. Convince yourself that when you actually switch all the inequality symbols, it still works. In any case, we have now proven the weighted mean value theorem for integrals. Now this isn't a theorem that you're really going to be using in your practice, probably, but it is very, very, very important in establishing Taylor's inequality. In order to get to Taylor's inequality, if we look forward, here's Taylor's inequality, we do have to establish the Lagrange form of the remainder term. Here's one more theorem that we're going to introduce, and we're going to kind of pseudo-prove. I say pseudo-prove because there is going to be one step in this theorem, or rather in the proof of this theorem, that we won't necessarily be able to prove, and that's, well, not necessarily true. We could prove it, but it would require a proof strategy called the principle of mathematical induction. The principle of mathematical induction is something that we don't always cover in a thorough process, but if you are going to be going into any sort of analysis when you go further in your mathematics courses, then this is absolutely a concept that you would cover, and I would encourage you to come back and prove this statement using the principle of mathematical induction. But because that's not really something that I'm going to assume all of you are familiar with, it's a step that I don't necessarily want to go further into. So I will point out what step that we're actually going to be bypassing, but just know that you have the ability to go out and find the principle of mathematical induction, sometimes called PMI, and sometimes just called proof by induction, but we are going to just assume one step. So, let's talk about this particular theorem, and then let's prove it. So it says, if you have an n plus first derivative, and that n plus first derivative is continuous on some open interval I containing the number a. So what that means is that if you have a number line and you have the number a, then when you zoom in on this, you're going to have some open interval containing a, and this open interval is going to be an interval on which f is continuous. So, if you have some open interval containing a, and x is somewhere in I, so x is somewhere in this interval, then there exists some value c between a and x. So, we have c being some value between a and x. If this is the value of x, then c is somewhere in here. There exists some value c between a and x such that the remainder is equivalent to the n plus first derivative applied at c, not at a, but applied at c, over n plus 1 factorial times x minus a to the n plus first power. we actually have a name for this. We call this the Lagrange form of the remainder term. Now this is, again, kind of a convoluted statement, something that, again, we're not going to be using in our practice too much, but it's essential for establishing Taylor's inequality, which actually is something that we will be utilizing. So to look forward before we prove this theorem, I want to point out that we have Taylor's theorem here. We will prove Taylor's theorem as well. And then we're going to be able to prove that e to the x is actually equal to the sum of its Maclaurin series. Remember in the previous video, we have this big question of if f can be represented by a power series. Now we can actually say that e to the x actually is equal to the sum of its Maclaurin series, not just a big if. And then I'm going to ask you to do this for sine of x. But a couple steps before we get there. So here's our Lagrange form of the remainder term. Now, the reason that we brought in the weighted mean value theorem was so that we could actually use that in this theorem. We have a function f. In this case, we're going to use the n plus first derivative of f instead of f, but we're going to need some function g because that's what the weighted mean value theorem actually used. So let's actually define a function g. I'm going to call it g of t. G of t is the function x minus t to the power of n. And this is a function defined for t in the closed interval from a to x. Now notice that this function g of t, the variable is t, it has only one zero. The zero of this function is x. Now, because t doesn't go beyond x, it's just to the left of x and actually equal to x at some point, this means that this function can't change sign. It is either always positive or always negative depending on what n is. So, this function, g of t, does not change sign on the closed interval from a to x. This is important because we do want to go back and notice that for the weighted mean value theorem for integrals, we have to have a function g that doesn't change sign on the closed interval that we are actually considering. So, g doesn't change sign on our particular interval. So, we can use the weighted mean value theorem. So, by the weighted mean value theorem, I'm going to abbreviate that with the weighted mean value theorem for integrals, there exists, let's go back up here and check what the theorem says. There exists some number c in our interval. So our value of c in our interval, this interval is a to x. What does this say? Such that the integral of the product of our two functions, such that the integral on our interval from a to x of the product of these two functions, our first function is the n plus first derivative, and our variable, be careful here, our variable is t, not x. The variable is t. So here's our first function, and g of x, which in this case is x minus t to the power of n, this is dt. This should be equivalent to, now, which function are we getting? F is the one that we are actually making sure that we plug in this value of c. So we're going to get an f to the n plus first. So this is the n plus first derivative at c. This is actually multiplied by the integral from a to x of x minus t to the power of n dt. This was from the weighted mean value theorem. Now let's go ahead and just evaluate this integral. Now the n plus first derivative at c, that stays the same. And if we find an antiderivative of x minus t to the power of n, then, well, remember our variable is t, so we're going to have an x minus t to the power of n plus 1 over n plus 1, but we want to make sure that we get this negative as well because the variable is t, and t is negative in here. We want to make sure that we get that negative as well. So we have a negative in front, and this gets evaluated for the value, and I'm just going to be very careful. Our variable is not x, so I'm going to write t. The lower limit was a, and t, the upper limit was x. Now if we plug these in, we should get a negative n plus first derivative at c multiplied by, well, x minus x. Well, that's going to be 0, so plugging in x is equal to t will result in 0. So then we subtract the result of what happens when we plug in a, which is going to be an x minus a to the n plus first power over n plus 1. We can simplify this a tiny bit. This is two negatives, canceling to be a positive. So we get an n plus first derivative at c multiplied by x minus a to the n plus 1 over n plus 1. Now, what are we trying to show here? We're trying to show that the n plus first derivative at c times x minus a to the n plus first power all over n plus 1. Well, we want to show that if that n plus 1 had a factorial, then that's the remainder. But that's not necessarily what we have just yet. And this is where this big asterisk comes in that I was talking about before we started proving this. I'm going to keep this in purple just to say this is a statement that we didn't prove. But we could prove using the principle of mathematical induction that the remainder is actually always going to be equal to 1 over n factorial times an integral from a to x of x minus t to the power of n times the n plus first derivative at t dt. This is a fact from analysis that we could use, but it's just slightly beyond what we want to do. But we still do want to utilize this. Now notice that this integral matches with the integral that we have right here. So we can actually replace this integral with the result that we found there at the bottom. So we can say that the remainder is 1 over n factorial times the n plus first derivative at c times x minus a to the n plus 1 over n plus 1. Now notice we have a denominator now of n plus 1 times n factorial. And n plus 1 times n factorial, that's just another way for saying n plus 1 factorial. So this is 1 over n plus 1 factorial times the n plus first derivative at c multiplied by x minus a to the power of n plus 1. And this actually is completely equivalent to what this theorem is saying that we should get. So, we've shown exactly what we're supposed to show. Perfect. We're on our way. Alright, so Taylor's inequality. This theorem says if we have the absolute value of the n plus first derivative at x is less than or equal to some value of, let's call it big M, for all of the x values such that the absolute value of x minus a is less than or equal to a number d. Now normally we use the number r here, but r is kind of taken with our remainder, so we change it up and use d instead. Taylor's inequality says if this happens, then the remainder, r sub n, of the Taylor polynomial actually satisfies this inequality. This is really useful to say because this is just a little bit easier to work with, and later on we're going to be wanting to show that the remainder goes to 0. Now, the remainder, finding the limit of the remainder, sometimes is a little bit difficult because the remainder is an infinite series, but this is a single term, and this is a little bit easier to work with, especially in computing limits. So let's see if we can prove Taylor's inequality, and then we'll actually be able to use this theorem and hopefully show that some functions are actually equal to the sum of its Taylor series. Now the proof is actually not so bad because we've already done a lot of the setup, so let's just finish this out. From the previous theorem, the Lagrange form of the remainder, we know that r sub n of x is equal to the n plus first derivative at c over n plus 1 factorial times x minus a to the n plus first power. So we can take the absolute value of both sides of this, and that must still be true, the absolute value of r sub n of x, and we're doing this because we see an absolute value of r sub n of x over here. So let's take the absolute value of r sub n of x, which means that we're taking the absolute value of the n plus first derivative at c over n plus 1 factorial times x minus a to the n plus first power. But notice that the denominator here, the absolute value, or the n plus 1 factorial, that's always positive, so I don't actually need that inside of an absolute value. The n plus first derivative at c, I don't know whether that's positive or negative, so that absolutely does need the absolute value. And the x minus a, that absolutely could be negative, so we need to make sure that that also contains our absolute value. This is what the absolute value of r sub n looks like. But we are assuming that since the absolute value of the n plus first derivative at x is less than or equal to big M for all x values such that the absolute value of x minus a is less than or equal to d. Since this is true, and c is a value between a and x, this means that c is a value such that the absolute value of x minus, this means that c is a value that's actually in this interval, so the absolute value of c minus a is less than or equal to d. And this means that we can actually replace the absolute value of the n plus first derivative at c, well, not replace, but say that this is actually less than or equal to m. So, because we know that the absolute value of r sub n of x is equal to the absolute value of the n plus first derivative at c over n plus 1 factorial times the absolute value of x minus a to the n plus 1, that we can actually replace this numerator with just an m, as long as we know and keep in mind that m is a value that is at least the size of the n plus first derivative at c. What this means is that we can actually say that r sub n of x in size is less than or equal to replacing this value with an m. Nothing else changes. we're just replacing that numerator with an m. Now this value of m may be larger than the absolute value of the n plus first derivative at c, so we make that compensation by changing that equals to a less than or possibly equal to. Now this is astounding because this is the exact statement that we were trying to make. So we've proven our theorem. We've now just proven Taylor's inequality. So what does this all mean? That's still a very, very valid question. So here's what this means. These theorems go together, show that if the n plus first derivative at c over n plus 1 factorial times the absolute value of x minus a to the power of n plus 1 goes to 0, because this is at least the size of the remainder. So if this goes to 0 for all x in the interval from a to x, then this shows that the size of r sub n of x goes to 0 as well. And so f is the sum of its Taylor series. So in this next problem, it says prove that e to the power of x is equal to the sum of its Maclaurin series, which is a Taylor series. That what we need to do is we need to show that this is true. We keep changing the question. We started with if f of x can be represented by a power series, so the question is when can f of x be represented by a power series? We answer that with f can be represented by a power series, or a Taylor series, when the remainder goes to 0. So the new question is, when does the remainder go to 0? It took some time, but we finally were able to answer that. The remainder goes to 0 if this quantity here circled in red actually goes to 0. This is advantageous because it is something that we can concretely compute. So let's actually prove that e to the x is equal to the sum of its Maclaurin series, and we do that by showing that this is true here in the red. Alright, we claim that f of x, which is equal to e to the x, is equal to the sum, as n goes from 0 to infinity, of x to the power of n over n factorial. Now we want to use the Lagrange remainder to actually show, that r sub n of x goes to 0, and we want to use the Lagrange remainder because r sub n of x is actually equal to an n plus first derivative at c over n plus 1 factorial times x minus a to the n plus first power. Now in this case, f of x is e to the x, and a is equal to 0 because we're using a Maclaurin series. So r sub n of x is going to be an n plus first derivative of e to the x. Well, any derivative of e to the x is e to the x, so that's cool. We can just get e to the x, or in this case, we're plugging in c, so we're getting e to the c over n plus 1 factorial times x minus a. Well, a is 0, so we get x to the n plus 1. Here is the Lagrange form of our remainder. So notice everything looked pretty complicated beforehand, but here we get a nicer expression. We just need to keep in mind what c is. C is some value between a and x. In this case, c is a value between a, which is 0, and x. And I actually see an error I made way up here in my note. In this green note up above, we wrote that this is the value of x. That should have been a c, isn't a and x. So here we go. Here's our Lagrange form of our remainder. Now, if d is greater than 0, and the absolute value of x is less than or equal to d, then e to the power of x is going to be less than or equal to e to the power of d. We want to introduce this so that we can actually utilize Taylor's inequality. We need to introduce this value of d. So e to the x is less than or equal to e to the power of d. And so Taylor's inequality says the size of the remainder, r sub n of x, is less than or equal, is equal to e to the c, which is positive, over n plus 1 factorial, which is positive, multiplied by x, which we're not sure, but let's just put that in absolute values just in case, to the power of n plus 1. Now, this is less than or equal to e to the power of d, because e to the x is less than or equal to e to the d, and c is a value of x. So e to the d over n plus 1 factorial times the absolute value of x to the n plus 1. This is true for all the absolute value of x is less than or equal to d. Now, since we know from previous video that the limit as n approaches infinity of x to the power of n over n factorial is equal to 0, it must be true that this part goes to 0. So, the limit as n approaches infinity of the absolute value of r sub n of x is less than or equal to the limit as n approaches infinity of e to the d over n plus 1 factorial times the absolute value of x to the n plus 1. That's equal to 0. So we've just shown that r sub n of x goes to 0. And this value of x happens, this is true for all values of x. So e to the x is always equal to the sum of its Taylor series. Sum as n goes from 0 to infinity of x to the power of n over n factorial. All we needed to do was to find that this is a true statement. And that's what we just did. So I want you to take the opportunity to try this with one more piece of information. Show that sine of x is equal to the sum of its Maclaurin series. Pause the video at this moment and try this out. When we're done with that, we will make one nice fun observation, just showing that e is equal to this. That shouldn't take too much time. So pause the video, try this out. Alright, let's see what we got. So we want to do the same kind of thing that we had done before. So we want to find the Lagrange remainder for sine of x, r sub n of x. We know that this is equal to the n plus first derivative at c over n plus 1 factorial times x to the power of n plus 1. In this case, f of x is sine of x, and a again is 0. Now, the n plus first derivative is either plus or minus sine of x or plus or minus cosine of x. All the derivatives of sine give you either plus or minus sine of x or cosine of x. The big thing to notice here is that what we're trying to do is we're trying to find this upper bound, this greatest possible value that the n plus first derivative could possibly be. Sine and cosine, never larger than 1, never smaller than -1, so the absolute value of the n plus first derivative for any value of c is never any bigger than 1. Now, I would actually encourage you, if you had a hard time getting to this particular point, maybe try pausing the video again, and then see if you can proceed from this point. And so I'll give you a few moments to try this out. Alright. So let's see what we got here. We are trying to find some sort of a relationship between the remainder and the Lagrange form of the remainder. Now, the remainder is the absolute value of the n plus first derivative at c over n plus 1 factorial times x in size to the n plus 1. But we now know that the n plus first derivative is never any larger than 1. So this is less than or equal to 1 over n plus 1 factorial times the absolute value of x to the power of n plus 1. And this says that our Lagrange remainder, r sub n of x, is less than or equal to the absolute value of x to the n plus 1 over n plus 1 factorial. Now again, we already know that the limit as n approaches infinity of x to the n over n factorial is 0. So when we take the limit as n approaches infinity of r sub n of x in size, this is less than or equal to the limit as n approaches infinity of absolute value of x to the n plus 1 over n plus 1 factorial. Because this is 0, we now know that the limit as n approaches infinity of the absolute value of r sub n of x is less than or equal to 0. But this is never negative, so this is greater than or equal to 0 as well. And so what we've determined is that the limit as n approaches infinity of the size of r sub n of x is equal to 0. So from our section on our video on sequences, we must know that the limit as n approaches infinity of the remainder is 0. And this is true for all x. Therefore, sine of x is equal to the sum of its Maclaurin series. That was a sum as n went from 0 to infinity of -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. And that proves it. It's no longer a question, it's definitive. We know that this has to be true. Alright, just want to finish up this video with one nice little bonus. We know that e to the x is equal to a sum, as n goes from 0 to infinity, of x to the power of n over n factorial. And this is something that we know to always be true. We've now proven it. That's what we did right here. One value that we know that this must be true for is if x is equal to 1. If x is equal to 1, then we get e to the 1 is a sum, as n goes from 0 to infinity, of 1 to the power of n over n factorial. Now 1 to the power of n is always just 1, and so we always get that e is a sum, as n goes from 0 to infinity, of 1 over n factorial. In the past, you may have seen e defined in several different ways. Another way that we've seen e defined is that it's a limit as n approaches infinity of 1 plus 1 over n to the nth power. This is another definition of e, but here's a new one. If you ever want the value of e, well, e is a sum of 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial, etc. And we know this because we have a series expansion for e to the x. We have a Taylor series for it, and we can now therefore try to do stuff with it. We can evaluate functions by utilizing series expansions. Here's one way to do that.